Oh. Hi, I'm back. So we're going to do an example here of radioactive decay, do a little calculation to show you how this works. And here's the situation. We've got 1,000, a box of 1,000 uranium-232 nuclei. Okay. Now this is not 238 or 235. This is a new uranium nucleus, and it's unstable. Okay, it's going to decay by alpha decay into thorium-228. And let's say that we have a box of 1,000 of them. 1,000 uranium-232 nuclei. Okay, so let me draw a picture here. This little graph. So this is number of uranium-232 nuclei. This is time. And we're starting off with 1,000 of them. Okay? Now let's say the date is April 17th, 1968, which isn't my birthday. I had my birthday last week, I wore my little party hat, so I figured I could use my birthday for this one. All right, so let me see if I can write 1968 correctly. 1968. So come back with me now, back to the 60s, between the assassinations of MLK and Bobby Kennedy. And that's when I was born. It's 1968, April 17th. And we have 1,000 thorium nuclei and 1,000 uranium nuclei, 232. Okay, and then we wait until last week, until until 4/17/2020 for a total of 52 years. Okay, so we started off when I was born, a box of 1,000 uranium-232 nuclei. And then last Friday, we opened it up and counted how many uranium-232 nuclei there were, and we found out that on the 17th of April, 2020, there were 593 of them. So we've gone from 1,000 down to about 593. So T equals 0 is 1968. Okay, so this time here is 52 years. We've gone from 1,000 to 593 uranium-232 nuclei. The question is, let me get a marker that's going to work here. What is the half-life of uranium-232? Okay, well, we're going to start with this. We're going to start with N equals N naught E to the minus lambda T. Okay. And we're going to solve this for lambda and then convert it to half-life. Remember, the half-life, I'll write it up here, the half-life, actually, it was the other way around. Lambda, I guess it really doesn't matter how we write it. Lambda is natural log of 2 over the half-life. So we're going to solve this for lambda because we know N is 1,000. We know N is 593. We know N naught is 1,000, and we know T is 52 years. So let's see how this looks. We need to solve this for lambda. How do you do that? Well, first you divide both sides by N naught. Right? Algebra-wise, you got to divide both sides by N naught. And then what we have to do is to get this exponent down into the main part of the math. What we do there is we take the natural log of both sides. So the natural log of n over n naught equals minus lambda t. Because the rule is that the natural log of e to the x is x. It brings the exponent down. You got e to the something and you want the something, take the natural log of it, it'll bring the exponent down. And so lambda is equal to the natural log of n over n naught divided by t, with a minus sign, right? And we know all those numbers. We know n naught, we know t, right? So once we have lambda, we can solve this for t1/2, the half-life. So this is going to be, let me get a better marker. My markers are really feeling the pain these days. Let's see. It's going to be natural minus natural log. N divided by n naught, 593 over 1,000 is 0.593. That fraction, n over n naught, is 0.593 divided by 52 years. And you don't have to convert this into seconds. Okay? As long as you, with problems, whenever you use this formula here, whatever time they give you, whether the half-life is in, whether you give you in milliseconds or whatever, you can just, as long as you're consistent with that unit, milliseconds all the way through, you're fine. If you give it to you in billions of years, you can use that unit all the way through. In this case, we're just given years, so we're keeping years all the way through, right? We're given years right here. We could have done it in days, but years is, if you just keep it with years, you'll be fine. We could have done it with any unit, but keeping it in years is the simplest. When you do this math here, you find out that lambda is equal to 0.01006. Okay? That's lambda. Do the math. Is positive because the natural log of a number less than 1 is negative. So a negative negative gives you a positive. Okay, and this is going to be inverse years, right? Lambda, where is it? Lambda is going to be a number over time, so it's going to be inverse time units, so inverse years. Right, we have a number on the top, natural log of 0.59 is a number, but on the bottom we have years, so it's 1 over years. Inverse year, same as year to the minus 1. So we can now write this. We can solve this for t1/2 is natural log of 2 over 0.01006 inverse years. And when you do that, you find that, and I've just about filled up the whole screen here, you find that t1/2 is about 69 years. Okay, so the half-life, that is for uranium, that is for uranium-232. That's the half-life of uranium-232. So by the time I'm 69 years old, which is, I guess, 17 years from now, we'll be down to 500 uranium nuclei left, not 593. Over the next 17 years, we'll lose 93 more of them, and it'll be down to half the original value, because that's what the half-life means, remember? And so if we started with 1,000, after one half-life, we'll be at 500. Then after two half-lives, we'll be at 250. After three half-lives, we'll be at 125, and so forth and so on, like that. Every half-life that keeps going, right? So our half-life here, then This half-life here is 69 years. The value here is 500. After another 69 years, okay, so that's 138 years. Yes. We'll be down to 250 of 200 after 138 years after April 17, 1968. We'll be down to a fourth of the original value, and so forth and so on. That's how you do the maths. See ya.